Good. Go back to your stat menu. Go back to your stat menu. Oops. I can't do that now. I just stay here. Go over to tests, just like you did before. Remember what the last one was called that we used last week? One prop zint. Yes, one prop z int, one prop zint. Very, very good. We're not going to use him. I mean, we're not going to use him because we're not interested in, say, the percentage of you that were higher than 10 or the percentage that were lower than 10. I want to answer the question, how well will a COCC student target 10 seconds? How close will we get to timing 10 seconds? That's a continuous data measure, isn't it? There. Timing, that's a continuous data measure. It's not yes or no, it's how close did we get. So let's figure out on average, how a COCC student would perceive 10 seconds. So we have to go to the T interval, which fortunately is pretty close to the top. There's one called a Z interval and there's one called a T interval. Remember how I told you some textbooks, they say if your sample size is 30 or below, use a T, and if it's above 30, use a Z. This is unfortunately a throwback to those days. If you go to Z interval, I'll go here and show you why you never want to use it, just so you know. Okay, notice the first thing it asks you to do is to input sigma, little sigma. At which case you throw your hands up and go, what the hell? I don't know little sigma. If I knew little sigma, what else would you know? You'd also know the whole population, which means you'd know mu, so why are you trying to estimate it if you know it? Unless you want to use government funds. I mean, but other than that, I mean, if you know mu, there's no reason to estimate mu, right? You getting that? So we don't ever use that guy. As a matter of fact, I'm going to give you a little hint. If you're ever sitting at home late at night trying to do a quiz or a project and you need to use your TI, you're never ever going to use anything with a Z unless it has a prop in it too. Because prop stands for proportion. And that's the only time I want you guys using the Z's in here is if you're dealing with proportions. So Z-test? No. T-test? Yes, we like T-tests. 2-stamp Z-test? No. 2-stamp T-test? Yes, we like those. So Z without a prop equals don't go there. Fair? I wish I could get in there and just take it away, but I don't know how to do that without invalidating your warranty. So go find the T interval. The T interval. Here she is. And the first thing it asks for is, do you have data or do you have stats? Now, what do we have? We have data because we just ran an experiment. Sometimes, though, you only have statistics. For example, this one right here, X bar, S and N, that would be statistics. So if you go over to stats real quick and press enter, you'll see where the places for those live. You got an X bar, you got an S, and you got an N. And look what it did. It actually called in the last bunch of data I crunched into there, which is actually kind of slick. So we have data, though. Let's pop out the data again. And it just asks you first where your data is. We're going to do 3 different intervals, even though that's statistically unsound for a reason we'll get to in a minute. But let's go to L1 first. L1. Its frequency should be 1, yes? Because we count each one of you one time. That's fair. 95% confidence okay with you guys? Yeah. Is that, I mean, please, Brandon.
Does it matter if it's 0.95 or 90?
No, it accepts either, just like my sample size program. Yes, sir. I mean, no, sir. It doesn't matter. Yes, sir. Good question. Calculate it. All right. It's thinking. Now, just so you know, these are generally going to take a little bit longer to calculate than the other ones. Do you know why? It's okay if you don't. It's a mathematical reason. Do you remember that formula that Gossett figured out by pulling the paper out of the hat? Remember how burly that thing was? It was full of what's called gamma distributions and factorials. Those are notoriously tough to mathematically calculate, even for a computer. So it took like 2 or 3 seconds for it to crunch that out, where the one prop Z in is like, boom, in a second it's gone. In less than a second, a fraction of a second. So just be patient with it. It takes a couple seconds. So there's your sample size of 22. There's the sample. You guys varied by 2.5 seconds on average. That's a whole lot of variance over 10 seconds, right? So here's your average. You guys average. Look at that. You average, according to this, 9.69. Almost exactly 9.7 seconds. That's not bad. That's not bad at all, is it? That's not bad. So let's put, maybe we'll go here. So, for a COCC student's estimation of 10 seconds. For a COCC's student's estimation of 10 seconds, let's swing this thing out. Trial 1, I am 95% confident that a COCC student calls 10 seconds at least 8.6 seconds, but no more than about 10.8 seconds. Is 10 in there? Yes, 10 is in there. 10 is in there, which means I can't prove that a COCC student is missing 10. Because 10's in there, right? This is, back to your look at my quiz, Chris, right? This would be an inconclusive study. If I was trying to show that COCC students were underestimating 10 seconds on average, 10 couldn't be in there. It would have to go something like 6.6 to 8.8 or something like that. Because then 10 seconds would be outside, and I could say I'm 95% confident COCC students are too much in a hurry, and they don't know what 10 seconds feels like anymore. This is inconclusive. This is inconclusive to me. Fair enough? Good. Very, very good. Very, very good. Let's do it after 2 trials. Let's run it a couple more times. After 2 trials. After 2 trials. And then after 3 trials. This is good. Back to stat tests. Let me swing the camera again. Oh, actually, you can see it okay. We're good. Still in the window. Back to the T interval. Switch it to L2. I want you to be considering some things we might want to consider about the data while I'm doing this. While I'm doing this, think about the numbers we've got and a consideration I might want to think about here. Okay, it's going to calculate. Take a couple seconds. Once you practice once, what happens? Now we go from 9.8 to 11. Look what happened there. What happened?
It shifted to the right.
It shifted to the right, which we actually thought was going to happen a little bit. The center is now at 10.4. Center's at 10.4. The box plots indicated that, right? The box plots indicated a shift to the right, moving to the right, which makes sense. I think we started slowing down once we saw it once. We're like, okay, let's learn from that. It's kind of like they put those flashing signs on 97 near the crosswalks now to get your attention, so you'll actually stop for pedestrians. Okay, you stop, or they put those and also the speed indicators on the speed limit signs. I can only imagine the brilliant effect that has. And then they blink. If you're going more than 10 over, they'll blink. I always try to get them to blink on my blink. I can't do it. Can't do it. That's superhuman speed. One more. L3. This is after 3 trials. What do we got? 9.7. 10.9. Very similar to 2 trials. All of which capture 10. All of them capture 10. Which means I don't get crazy. Remember the anecdotal evidence we had about, oh, I said 6, or oh, I said 15, right? The people that were worried that we were either too long or too short. The average kind of ignores the anecdotal outliers and deals strictly with the entire data set. Because outliers happen, yes? They exist in the world. We get them sometimes in the world. It's good. It's good to get them, okay? Please, Rory.
If you get a bunch of outliers, like a bunch of different times, can you average the outliers?
Now, let's talk about them. That's what I said. Think about something to consider when you're talking about data. So I'm going to come back in here for a second. I want to go back to those box plots. And I want to compare the box plots to these intervals. Can we see both on this? No, we can't. But if I back it out a smidge, we can. Okay. So here's the graph again. Is that recording? Yes. So this guy up here, if you look at where the center is, it's south of 10 a bit, maybe down by 8. It said the center was closer to 9. I got a feeling the reason it's closer to 9 and not closer to 8 is because we've got this long whisker here. So there were more people in, the top 25% of data was more varied than the bottom 25% of data. That evened out as we started working down a little bit. But that was an interesting little factoid. Then we get down to him. this guy here. And you notice how these guys have stabilized just like they were over here. These guys have tightened up, but we've still got outliers here. What I'd like you to do is to go into L2 and remove those two outliers from your data set. In general, I don't like doing this, but for purposes of illustration and to answer Rory's question, which is fantastic, by the way, friend, go in and pull out the two largest times in L2. I'll show you a slick little trick that'll help you find them pretty easily, too. If you go to Stat, and you go to Sort, either A or D. I think you might want to go Sort D. That's Sort Descending. Grab Sort D, and tell it, please sort L2 Descending, and press Enter. Now the data in L2 will go from biggest to smallest, which means you can just go in and delete the first two. Those are the two largest numbers. Is that fair? Hopefully that's fair. So now 14.1 and 13.28, if you'd be so kind to yard those two out of there, just delete them off. Because generally, you don't want to be as cavalier as this, throw it away! There might be a reason that those two are what they are. This is just kind of fabricated data, so I'm trying to deal with the theory of how to deal with these outliers versus why they're not there. So I'm going to hit delete twice. Delete. Delete. Now if you want, you can hit graph again. If you want, you can hit graph again. Notice they're not there anymore. They're gone. We got rid of them. Is that fair? Just hit delete twice. Rerun the interval without the outliers in it again. So we did it over here with the outliers in. Rerun it again. What effect will that have on the interval itself? Before you run it, what effect will it have on the interval, do you think?
Drop that 11 down.
Okay, the 11's good. The 11's going to be lower, right? Good. So down. How does an average react to outliers? This is a 243 question. It's a bastard move this early in the morning. What does an average do with outliers?
Water?
Yeah, well, that's the variation. Elizabeth, my second question. How does the variation change? It gets wider because there's more variation. Good. So suppose I taught 243. I taught you guys that the average on a graph is where you'd hold it if you were holding a plate of cookies. If you look at the distribution of the graph, it's where you put your finger to balance that tray. That's where your average is the finger. So suppose you're balancing a tray of cookies and somebody drops a cookie way on the outside. Where does your finger have to go to balance it? It moves towards the outlier. The average is going to chase the outliers. So if you pull the outliers off, the average is going to reset back more towards the chunk of data versus the individual outlier points. That's something we never have to concern ourselves with proportions. Because proportions, you can't be an outlier. Yes. No, that's it. Yes or no. There's no like, yes! It doesn't matter. It's yes or no. There's no like exceptional yes or medium no. It's 1 or 0, off or on. But with measurements, you can have outliers. That's the kicker. You can get far enough away from typical to be considered unusual. So that's just put that in the back of your mind for now. I got an experiment from Tuesday we'll deal with as well. Fair so far? So now let's rerun the interval on L2. Okay, give it a couple seconds. It was at 9.8 to 11, now it's 9.6 to 10.5. Lost a half a second on the top, Chris. Just like you said, the 11's going to come down. And it did. The average is now closer to 10 than it was. I believe it was at a 10.3 or 10.4 originally, whatever the halfway point is here. But it definitely came down. It definitely came down. And that's something to think about if you encounter outliers. I always like to figure out why they're there if I can. I like thinking about, okay, why is that goofy, unusual value there? If you remember in 243, we analyzed caffeine levels in energy drinks. At one point in one of the classes, I had 750 some soda. Depends on what you had. It was a couple terms ago, I didn't have this data yet. And it was a data set that had like 700 data points, and like 50 or 60 of them were outliers. Like there was an energy drink called like Drink This and Die or something that had like 1,000 milligrams of caffeine in 8 ounces. I forget what it was called. I've got it in my lessons somewhere. But I mean like 1,000 milligrams of caffeine. I'm like, holy shit. Like that's ridiculous. It turns out it was on the shelf for like 6 months and they pulled it. Because people were having heart palpitations after they drank it. So that's when you start looking at the outliers and why is that there? Oh, because somebody had a crappy marketing idea. Hey, I got a great idea. Let's make it unnecessary to sleep anymore. Great, people start dying on your products. You see, so that's why you start looking at those. And the reason I bring this up is because the outlier is going to be what the news reports on, unfortunately. right? I remember a news story not that long ago, this news article about how text messaging is driving up data usage in cell phone bills. And the one example, the anecdotal example they gave was a family who had a daughter that would send 1,000 texts a day. And we all shake our head. But we say, how typical is that? I asked my 243s, how many texts did you send today? 2/3 of the class say 0, and it is exponential. It goes like this. There are people that send 20 and 30 texts before noon. Nobody's even close to what it would have to be to get on track for 1,000, right? And if you look more deeply at that, and then you realize that's the exceptional case, there might be other things that draw up data usage and cable usage as well. For example, a lot of cartoons, I've learned this the hard way with Max, a lot of cartoons like Magic School Bus and things like that are being rebroadcast in higher def. Well, that uses more data. So I love the fact that occasionally he watches these things, but Jen's like, what the hell's going on? I'm like, I don't know, you watch Top Chef. And then I'm realizing that if they start putting it in high def and not telling you, they're sucking more of your data usage or your cable usage with kind of inadvertently. So other things can explain. Outliers are something to look at. Like, why is it an outlier? Why did this happen? More on that when we talk about cable usage as well. But mathematically, their effect is subtle, but also maybe meaningful, because he might pull an average somewhere where it shouldn't be logically. Let's try it with L3, because L3 had a couple, right? And they looked even more extreme than L3. You've got these guys and this guy. So let's pull those out and predict what effect it's going to have on 9-7 to 10-9. Kind of scratch down what you think it'll be. What do you think this interval will be if we take out those 3 outliers? And then we'll run it and see how close our guts. Remember, I like to think of 244 as a way to metric your gut. All right? My gut feeling, I've got an idea of what I think it's going to go to. Let's see how close I get. I'll write on a piece of paper, then I'll slide it over to the camera so you guys can see my guess. There's my guess. You guys got your guesses?
Mhm.
Cool. Okay, I'm going to go ahead and take out I'm going to sort my data. Stat sort D, L3. And now I've got to take out the top 2 and the bottom one, right? Because I got 2 tops and 1 bottom. So I'm going to go sort, edit, take out the 1425, take out the 1266, and also take out the, should have gone the other way. There we go. All right, let's take a look at the graph again. There he is. That's just beautiful. Absolutely, couldn't ask for better data. Thank you, guys. All right, here we go. Stat tests. L3. Oh my goodness! I'm not even close. That's what I guessed. I guessed 9-2 to 10-2. I totally underestimated the bottom. Only 1 outlier on the bottom and 2 on the top. I should have known. I should know better. 9-8 to 10-4. Oof. Hella close to 10. Look at the average, 10.1 essentially. Yeah. Pretty badass. Pretty badass.
What do we win?
Did you get it?
I got 9-9 to 10-5.
That's better than mine.
I got 9-9-10.
9-9-10-4, 9-9-10-2.
9-8-10-3.
Ooh! I think David's the closest. What should he win?
Around the clock.
A round of applause, Casey. That's a very good answer. It was like, great. Never has to do anything again, rule, without touching points to it. You guys are fantastic. Okay. I think we'll stop there after one more Monte Carlo thing to show you guys, because the experiment I have left is going to take more than 10 minutes to get, so we'll do it first thing on Tuesday. But I did want to share one last thing with you before you got out of here. It's a little spreadsheet I developed, and I'd be happy to give this to you guys if you want it. It's the idea, you can't see it right now, hang on. Turn the screen on.